So good afternoon, everyone. I can see that we've got also some people from the American continent. So good morning to those, good afternoon to the one in Europe, and good evening if there are any people from Asia. So it's a great pleasure for me to introduce this webinar, and I will be hosting it for you. We've got two great scientists instructing that webinar today. So I will introduce them to you in the order of appearance this afternoon. So first, I would like to introduce you Sophie Fischer-Olshausen, who joined 𝐬𝐴 Lab 2 years ago, and she's working as a consultant in the PBPK group. She had a master's degree in biophysics in Germany, and then she followed up with a PhD in Professor Susanna Roblitz's computational system biology group in Norway. And she helped develop a mechanistic model of the menstrual cycle endocrine regulation. And before joining 𝐬𝐴 Lab, she worked for a little while as a pharmacometrician at AstraZeneca in Sweden. And Sophie is passionate about women's health, and she leads the initiative which are related to women's health at 𝐬𝐴 Labs. And then after Sophie, you will see Nina Nowalart. Nina joined 1 year ago 𝐬𝐴 Lab, and she's also working in the same group as Sophie. She holds a master's degree in drug development from the 𝐏𝐬𝐈 in Belgium, and she had a PhD in drug delivery and disposition group from the group of Professor Peter Anhart. And her PhD was part of the IMI project conception, and during that she specialized in developing and applying in vitro and PBPK model to investigate drug exposition in lactating mother and their child. And at 𝐬𝐴 Lab, she focuses on special population and advancing research in women's health. So no mystery that they work together to prepare this course and also this webinar. So before I give the floor to them, I would like to say a couple of things. So there will be a break during the webinar, 5 to 10 minutes, depending on how things goes. And also, and I saw that many people already found the way. So ask the question in the Q&A, not in the chat, but it seems that the chat is disabled anyway. So with that, I think we're all fine. And so when you're asking questions, we will answer them as the presentation goes. And then at the end, normally, there should be more time for question at the end of the webinar. So without further ado, Sophie, the floor is yours.
Thank you for the introduction. Do you all see the right screen with the slides?
Yes.
Perfect. All right. So yeah, I think I can safely say that Nina and I are quite excited to have this opportunity today to give you a bit of an idea of our modeling activities around exposure modeling in the organs of the female reproductive tract. And yeah, we're quite happy that so many people took the time out of their day to join us today. And yeah, we hope that we can empower and enable you to actually use that in your modeling project as well. So what we will do today, we will start with a short introduction. I will tell you a bit about what we're doing, but also what's the aim for the workshop today. I will give you a bit of like general content, but then move into a more specific content for the hands-on exercise. We'll have a short break, and then I hand over to Nina, who will walk you through a hands-on exercise, and then in the end, we will have hopefully a bit more time for questions and wrapping up things. So yeah, about 𝐬𝐴 Lab. So the name is inspired by the Latin god of medicine, Aeschylus. And if we combine that with 3 elements that are important to our work in drug development, efficiency, safety, and quality, we'll end up with Aeschylus. So yeah, that's kind of the story behind the name. And since 2017, it's a growing team of scientists that have been supporting decision-making processes in various research and development projects in the pharmaceutical and chemical industry. And our services focus mainly on 4 areas. It's model-informed drug development, so using models to support internal and regulatory decision-making throughout the process of drug development. It's next generation risk assessment, which is the application of mathematical models to assess the risk of chemicals. We are a very important contributor to the development that happened in or for the open systems pharmacology suite. So it's an open source software framework to do PBK and QSP modeling. And lastly, we develop training material and tailor trainings to enable scientists to do modeling for their projects. So very central piece is PBK modeling, and it's also what we will talk about a lot today. And PBK modeling is a mechanistic modeling framework that integrates drug-specific data and system physiological parameters to simulate absorption, distribution, metabolism, and excretion of drugs in humans and animals. I kind of like to think about it as represent the body as kind of a collection of containers which are distributed by the bloodstream. And then a compound, a drug, or any chemical really will kind of travel around, move by the bloodstream. But in each container that would represent a given organ, there could be, for example, a reaction happening and kind of change something about that compound. And that's kind of what we try to capture with PBK modeling, understanding the fate of a drug. And in order to do that bottom-up modeling approach, we need various types of parameters. The first class are organ-specific parameters or organism-specific parameters. That would be things like organ volumes, blood flows, tissue compositions. The second type of data are drug-specific data. So, for example, lipophilicity, molecular size, those types of things. The third class, I kind of like to think about them, that bridge between the compound and the organism, for example, the fraction unbound in plasma, or the capability of a compound to partition into different tissues. And the last element we need knowledge about is kind of the exposure, characterizing the exposure, the dose, the way of exposure, was it dermal or inhalation or oral, and also were there other events that could have or that could affect how that drug or chemical compound would be what's the fate of that compound. And the open systems pharmacology suite gives us a very tailored modeling environment to actually address those exposure questions and integrate all that knowledge and information from various sources. And so, it's very suitable for PBK modeling, but also allows a lot of model adaptation and extension. So to allow you to tailor your model to your specific application, or for example, if you want to not only know exposure, but also drug effects, those softwares can be quite useful. So it's kind of two. The first part is PKSIM. It's an intuitive model builder, very much built to enable people to do PBK modeling. So it's quite easy to use. There are a lot of predefined things you can work with and build up on. And there's a knowledge database behind it that will help you to set up your models. But having that idea of having a very user-friendly software interface kind of in mind, it comes a bit at the drawback of there's less maybe user freedom in a sense. So you can't change all parameters easily, and maybe not all information is accessible right at that point. And then there's the second software in the open systems pharmacology suite called MOBI, and it's more advanced model builder. So here you will have access to all the information you would like to have of your model, all the parameters, and set up in a way that models can easily be reused, or model parts can be reused. And there's really a lot of flexibility. So everything you would like to describe in terms of something changes over time, express it as an ordinary differential equation, could be implemented in your model through MOBI. But that comes at the price. I guess a lot of flexibility comes often as a price. So here at the price, you don't have so many predefined things you can just use. So so it's maybe a bit of more time to invest to be very familiar with how to do things. But today we will show you a kind of simple application case where we use MOBI to extend a PBK-based model and add additional organs to it. yeah, so that's kind of our objective today. We want to extend a whole body PBK model as it is available in the Open Systems Pharmacology suite to also present the organs of the female reproductive tract. And because that's the way that will help us to understand exposure in those organs. So the general PBK model, as it is in the Open Systems Pharmacology suite, has all the yellow, blue, and red organs. So it's kind of the base model. So it doesn't have any compartments that are female specific. So what we wanted to do is we want to develop a way to extend that base model to also present female specific organs, especially the vagina, the cervix, the uterus. Because those organs, they are quite important for female well-being and female health. So they're essential for reproductive health, sexual health, but they're also involved in endocrine regulation. And so there are quite a number of treatments that will target those tissues. To just give you an idea about it. So I guess maybe what's like the most obvious thing is the area of contraception, but also fertility treatments. There are a number of medications that will be administered orally or as injections to either have a contraceptive effect, but also to they are integral parts of in vitro fertilization assays. So but on the other side, there are also other diseases like cervical cancer that will be treated and where the treatment target is very clearly those organs. And beyond the scope of giving drugs systemically to treat something in those tissues, the female reproductive tract also has abilities for local administration routes. So for example, estradiol can be administered as a ring to treat menopausal symptoms, or vaginal creams or gels can be used to treat infections. And there has also been a vaginal ring being approved for HIV prevention treatment. So overall, I think there's kind of like a wide scope of possible applications, but would be very interested in predicting exposure in those organs. So that would be contraceptive and reproductive health, but also treatment and prevention of infections, fertility treatments for menstrual and hormonal disorders, as well as symptoms of menopause that need to be managed. There are a number of cancers in those regions as well that needs treatment. And there's also the area of pregnancy and postpartum complications that, might require treatments. So what we want to show you today is how you can extend your base PBK model to present the organs of the female reproductive tract. And so we'll show you how you can edit and then run simulations. We will look at one kind of like test compound for today, and that's metronidazole. And metronidazole is a compound that is very widely used to treat infections. And in the area of like female health, it's mainly used to treat vaginal infections, for example, via oral dosing, but also intravenous dosing or vaginal dosing. To give you a bit of like background about pharmacokinetics for that compound, it has an oral availability of about 90%. But if you go for example, an vaginal administration, predicted availability or expected availability will be lower, maybe around like 20 to 50%. It's an hydrophilic compound with a large distribution volume, and protein binding is below 20%. If we look a bit about in its metabolism and excretion, so it's metabolized in the liver through 3 different pathways, and 60 to 80% will be of the compound itself, as well as its metabolite will be eliminated through the kidney. Yes, so that was kind of like a bit of an idea of what type of compound we're looking at. So it's something that's quite established to treat infections. And the example for today will be an IV administration of metronidazole. And then I guess the other like main important part of today's webinar that you should learn about before starting in the hands-on is the actual extension module that we developed. So we really wanted to have a PBK model that can present the organs of the female reproductive tract as like explicit containers, let's say. And so The organs we're mainly focusing on is the vagina, which is a muscular channel that connects the external genitals to the cervix, which is the lower part of the uterus. It's kind of the connection between the vagina and the uterus. The uterus, which is again a muscle type of organ that is composed of the myometrium and the endometrium, and the endometrium is kind of the inner lining of that organ. It thickens over the menstrual cycle and kind of prepares for a fertilized egg to arrive. Yeah, and the uterus is also like the place of fetal development, but in cases if there's no fertilization happening, the uterus, this inner lining of the uterus will be shattered during menstruation. And then lastly, we also have the ovaries and the fallopian tubes. So the ovaries are small glands that are very important for oocyte maturation and release of oocyte that will then travel through the fallopian tubes to the uterus, but also the ovaries have an important role for hormone production. But for our PBK model extension, which you can generally use to extend any PBK model that is available in the Open Systems Pharmacology suite, as long as you work in MOBI version 12. And then, yeah, you can use it to predict exposure in those tissues. The structure or the module is available on GitHub, and you're very welcome to use it. Yeah, but this extension comes as like, so what it actually includes is the breast compartment, which is not necessarily not part of the female reproductive tract, but it was also missing in the base structure. So we included it in that like scope of tailoring the PBK model to present female physiology. And then further we included the myometrium, the endometrium, the cervix and the vagina, as well as two fluid compartments, the uterine fluid and the vaginal, cervical vaginal fluid. The fluids are very important to be able to actually predict exposure after local administration, because that's like how things will actually be kind of diffused from the administration device into the tissues. And yeah, maybe it's like a little disclaimer. We did neglect the fallopian tubes and the ovaries in our structure because there was very little data available that would have allowed us to actually describe those organs in a manner that it would be meaningful for the model. It would be great to include them, we were just not having the right data at that point. But it would be something that would be great to add. Yeah, so I think that's kind of that part. Yeah, so we touched on that before, so local administration, and that's kind of the last part or the last element I want to touch on today is, yeah, local administration. I think it's quite an interesting topic because there are true benefits to administering drugs locally. So if those tissues are the target, it's quite useful because we avoid first pass metabolism, which can be quite useful depending on the compound. But also we make sure that we have the concentration that we need in the tissues that we needed while keeping local exposure lower, which means we could also have less side effects. And generally, I guess there are mainly two routes discussed for local administration in that context. It's vaginal and uterine administration, but also cervical administration would be an option. So for vaginal administration, there are quite a lot of formulations available, but the most typical ones are tablets, creams, gels, and rings, I would say. And then for uterine exposure, it's mainly used in the context of contraceptive, and then it's a uterine device that like sits in that like cavity, in the uterine cavity. And lastly, cervical routes could generally be of interest, especially for the treatment of cervical cancer. Yeah, I think that was the introduction from my side so far. I think, yeah, we could, yeah, if there's already something burning, we could take questions now. Otherwise, I would invite everyone to opening PKSim and MOBI and also the training platform so that we are all set to, yeah, go after the break.
Okay. So I hope everyone is back. And I hope that you've got your PKSim and MOBI ready. So Nina, the floor is yours.
Okay, so can you hear me well?
Yes, very well.
Okay. So I will show you the hands-on part for this exercise. So you will need, as already mentioned, PBPK, Mobi, and ideally also the link you received for the training platform and the 𝐏𝐁 files and modules that were sent to you. If you don't have it, you can also follow my screen, so that's not a very big problem. So in this hands-on part, we will not go into the basic model development, but if you're interested in that, you can go into the full course via our learning platform and also check out how to develop a PBPK model. Here we will start from a PBPK model that is already fully developed and working. So, and I put here also the title of the section in the training platform, and we will go through step by step. So if you go into PBPK, you will see on the left top corner this file option. You can select open, and then you can navigate to this material that you received via the email. And in the catch-up point, you should find this FRT1 file, and that's the full PBPK project file. So very briefly, for those of you who are not familiar with PBPK, so we have on the left here a building block navigator and a simulations navigator. So in PBPK, we work with different building blocks that you can then combine in different ways to form different simulations. So the most important one usually is your compound, where we have here metronidazole as our example compound. If you open it, you will see 3 different tabs. So you have the basic physicochemistry, then we have some atomic properties, and then more advanced parameters that we, for this simple example, are not using. So in the basic physicochemistry, you will find the lipophilicity, which has a value of minus 0.02 here. Then you will find some information related to the fraction unbound. So here it binds to albumin with a fraction unbound of 0.89. You will also see the molecular weight with the option to indicate if there are halogens present in the molecule. Then the compound type and pKa values, so it's the base with the pK of 2.49, and information related to the solubility. So in this case, we assumed a very high solubility, which is very close to reported values. Then you have the atomic properties, which has some information related to absorption, distribution, metabolism, and excretion. So for absorption, we're not really using it in this exercise since it's intravenous, but you have the specific intestinal permeability that is calculated by default. You can find the distribution methods that are used for this model. Then we have the metabolism information. So like Sophie presented earlier today, we have 2 enzymes that we included in this model, so CYP2A6 and CYP3A4, which have an equal contribution to the metabolism. And then there are a bunch of other enzymes that we did not specifically model in this compound, but which are combined together as a total hepatic clearance, which represents then the remainder of the metabolism. And then finally, we also have renal clearance in this model. So you can go into it and have a further look if you like, but just to keep it brief here. Besides the compound, we also have an individual here. So that's a typical 30-year-old female, an European female in this case. And you will also see the expression profile. So for each individual, we will always need to link the expression, which you can load from a database that is available. So here we have the 2 enzymes. And then the final building block that we have that is relevant here is the administration protocol. So if you open that one, you would see that we are doing here an intravenous infusion of 500 milligram
administered over 20 minutes. You can also go for other administration types or more advanced protocols. But basically, if you have these standard building blocks, you can combine them into a simulation, and that's what you see in the simulations navigator below. So if we open that one, you will see already a simulation, which if I configure it quickly to show, so it's a combination of the different building blocks, so the female woman, the compound, it has all the different processes that we described, and administration of intravenous application. So in the exercise, we will immediately go into saving this project. The reason for that is just if you decide at some point later on that you want to make a change to this model, it's easy to go back and you could easily just transfer again an updated model to MOBI and have it easily combined with the modules and the changes that you made in MOBI without redoing the entire workflow. And then so if you want to save it, it's File, Save, Save As. And then you can give it a name, so you can call it my female reproductive tract project and save it in a location as you prefer. And then you can export this simulation to MOBI. So we always start or attempt to start in PKSIM because it's easier to make a standard PBPK model, but then for doing these more advanced topics like the female reproductive tract, we need MOBI. You could also directly start in MOBI, but it's a lot more difficult to create full-based PBPK model in MOBI. It's not wrong to do that, but it's just easier to just do it in PKSIM and then export it. So you can right-click on it and then select the option Send to MOBI. And if you click on this one, it will send the entire model to MOBI. And it can take a few minutes depending on how fast your laptop is. So you will see this screen indicating that it is running. So if there are any questions or issues that you have, please put them also in the question and answer, and then we will try to help you also. So going back to the slide, we have now exported the simulation to MOBI, which is relatively easy if you already have a PKSIM model. So you could do exactly the same for any compound of interest for your projects. And then the next step is to add this extension model for the female reproductive tract. So we developed this module. We have it available already on GitHub, where you can just download it, or we also provided it via the training material, and then you can just load it directly in MOBI. If we go back to MOBI. So in MOBI, you will now see this blue module, which is a PKSIM module. So that is just the model that we exported from PKSIM. And you will also see the individual and the expression profile as a separate building blocks here. And similar to PKSIM, below you have the simulations explorer, where you will also find your simulation. So if you would run this one, it would give you exactly the same result as you got in PKSIM. Now, if we want to adapt a model, we have this new modularization concept in MOBI since the latest version, which makes things much easier. So for the ones who worked with the old versions of MOBI, you would have to start manually adapting your structure of your PBPK model. Here you can just keep this PKSIM module and you will have a separate module which has all the extensions or modifications. And once you go create a simulation, you will tell the software to combine both of them, and it will make a combined PBPK model with the entire structure containing your PKSIM module and your additional extension or overriding modules. If you want to make like a new one, you can do create module. Here we already have the module available, so you would just select, if you right click on modules, the load module option. So then you go towards the extension modules that were provided, and you will see this 2 extension modules. So as Sophie mentioned, today we want to focus just on the female reproductive tract with still systemic administration, but you could also do local administration, and we have some examples of that also on GitHub and in a training course with, for example, this cervicovaginal administration module. Today we will not use that one and just use the female reproductive tract module, so you can open this one. And then you will see in Mobi that there is another module showing now, which has this orange icon indicating that it is a Mobi module. So that's to differentiate between what is a Mobi module and what is just a PBPK module.
Nina, let's just wait 1 minute to make sure that everyone was able to download the module.
Yes. So if there's any problems or if I'm going too fast, please also put it in the Q&A and we can help you or go a bit slower. So what you will see in this PBPK module is that there is a lot more building blocks compared to this extension module. So the PBPK module, I think related to the question asked before, is a full PBPK model and it can be used to do a simulation by itself. For this extension module, you cannot do a simulation just with this extension module because it doesn't contain all the required information. So it always needs to be combined with this basic PBPK module, and that can be really for any project or any compound that you can just combine it. And for example, if we go into the organism, which has the structure and the containers, if you look at the PBPK module, you will see here all these default organs present, whereas if we go into the extension module, you will see that we only have the specific female reproductive tract organs present here. So they will be combined and added on top of the standard PBPK model. So loading this module is the first step. Right now, the module already has all the structures, but it doesn't have any information related to the compound. So if you want to use this module, it's relatively fast and easy. There is only the step of loading it, and then you need to add a few parameters that are specific for your compound in the female reproductive tract and set the initial conditions so that the module can be run. So the next step will be to add your parameter values then. So you see here that there is already a parameter values building block present. And if we open that one, you will see that we called it default parameter values. So all the parameters that are required for this compound or any compound in this female reproductive tract are here. But of course, the values need to be adapted to your specific compound. To do that easily, you can make a clone of this building block. If you right-click on it again and select clone, and you can give it the name of the compound, for example. And then you will have exactly the same. The advantage is that you can do this for multiple compounds in the same module, so you don't have to load the module again and again. If you want to simulate different compounds in the same file, you can just have different parameter values building blocks. So what we have here is this scaling for the fraction unbound. For this compound, we're not using it, but for example, in some cases when there is a very high local target binding, it could be necessary to use a scaling factor therefore, so we have added this option here. If we keep it to a value of 1, it will not scale anything, and it will just be the normal fraction unbound in the tissue. Then we have a diffusion coefficient for the diffusion between the fluid compartments and the tissue compartments that are present in this module. So we see that there are 3 connections. And then lastly, the fraction unionized in the fluid compartments. Ideally, you would have in vitro or in vivo values for all of these parameters, but if you're a bit familiar with the field, you might already know that often this is not known or not available, and it's not that easy to just generate all of these things. So therefore, we also provided some R scripts that can be used to give you an initial estimate of these parameters in case that the data is not available, which is also what we are using here for this compound. You can find the full R scripts on GitHub if you want to use them, but we're not going to go into the details of that. So if you look in the training material, you will see that the fraction unionized is actually 1 in both fluids for this compound. And then you can adapt the value for the diffusion coefficient. And don't forget to also adapt the units to the right ones. And you will see that we have the same value for the 3 diffusion coefficients. So in these parameter values, you also have the option to define the origin of your value if you want to keep track of where you got it from. So whether it's an estimate or an in vitro value, you can all track that here in the source column and keep track of things a bit more.
So Nina, the value is 2.3 e to the minus 6, yes?
Yes.
Thank you.
Okay, so I hope everyone is able to follow so far. So now we have our module, we have the parameter values for this compound. Then there is one last thing that we need, which are the initial conditions. And just to give you an idea of what this is, I will open the initial conditions in the base PBPK module. So there you will see that for the compound and also, for example, for the metabolites, you have these initial conditions in each of the different compartments that are present. And almost all of them have a value of 0. So what does this exactly mean? This means that this compound can be present in this compartment, but when the simulation is started, it has a value or an amount of 0 in a specific compartment. It is important to still have this initial condition, because if you don't put the 0 value there as a line, it will not be allowed to travel to this compartment during the simulation. I see that there is a question. You have some options to export some of the things from a simulation into a text file, which is not entirely complete ODEs, but which has all the different formulas available. And you can also, in Mobi, travel through these building blocks and find all the parameters and all the equations that are behind it. Yes, so for our parameter values for this specific compound, we indeed assume that it has the same behavior, or at least the same fraction unionized and diffusion coefficient across these different compartments. It depends, for example, for the friction unionized, these 2 fluids have a different pH value, so it depends on the pK. So here it's both 1, but it can be different for some other compounds. And similar for the diffusion coefficient, it's also related to the fact that we don't have very specific data for any of them, but they can definitely be different, which is also why they are included as separate parameters and not just a single parameter. So if you want to extend...
Yes, I'm just reading the question because I think if people don't read it. So someone is asking, how do I automatically import parameter into the software?
Yes. So for example, for this parameter values here, what you could do if you right click on it, you can click export to Excel and you can create an Excel file, and you could then also adapt the values in the Excel file and also reload them later from Excel. So that's a way to automatically import parameters, but it's per building block that you can import things. So you cannot just import parameters for the entire PBPK model and module. It's always a bit specific. And the R script can be found on the GitHub. So we will also show the QR code again later. Okay. So if we want to add the initial conditions, there is this option. So you will see that we don't have a building block with initial conditions in our female reproductive tract module. So you would right click on it and select add building block first. And then here you can select the initial conditions, and you can also give it a name. So it's always easy if you name it according to the compounds. You see that you can also add other building blocks if you would like to, but you're not obligated to have all the building blocks under one module. So now we have this initial conditions building block, but you can see it's still empty. So to add now more or less automatically for our compound, you can right click on the extend option here in the left top corner. And then we see here the selection of the spatial structure. So we have our base PBPK model or the female reproductive tract module. So we will select the female reproductive tract because we want to add the initial conditions for these female reproductive tract organs and not for the organs that are already present in the base module, because there we already have them. And then you can select here the compound. So as you can see, you can add initial conditions for the enzymes, for the compound, and for the different metabolites. In this case, we will assume that there is no metabolism happening in the female reproductive tract. So related to the question as before, you could add also metabolism, and then you would, for example, add these enzymes, but then you need to have also expression available for these specific enzymes, which at the moment is not in the default database and also in general not really available. If you would have this type of data, of course, you could add expression locally and also add the enzymes in the female reproductive tract here with the initial conditions. So for today, we will only add our compound itself, so metronidazole. You can select it and then click on OK. And then you will see that there appears for all the different organs that we have, with also the different sub-organs, this line which all have a value of 0 and is present selected. So this tells our software that the compound can travel into these different female reproductive tract compartments, but when we start the simulation at time 0, the amount will be 0. And with that, we actually already did all the steps that you have to do to set up the building blocks. So it's very easy to do if you are using this type of existing modules. It's not a lot of work, especially if you get used to this type of working. You can really do it in maybe 10 minutes. And then we can start thinking about doing a simulation, and we want to compare it to observed data. So the next step that we would do is to add observed data. So here you have the observed data module. If you right-click on it, you can select Add Observed Data. And then you navigate again to this material that was provided, and you will find this Excel file which has observed data that we collected for the female reproductive tract for our compound. You can open it, and then it will import the data. So what you see here on the right, we have two tabs because we have data from two different sources. So today we will work with the one from Manisto. So you can click on it, you can have a look. So you see we collected, for example, the study ID, information related to the organ, the compartment where the sample was taken, but also information about the dose and even some information about the population that was used in this article. And then you will find the actual measurements, so the time with the units and the measurement with the units and also the error that we have. So what we tend to do is use this default the same structure for the observed data files, and then you will see that a lot of it is automatically already mapped. So the software tries to recognize what exactly these columns are. So the species, the organ, the compartment is already mapped correctly, but I always recommend to have a look if everything is correct. There's a few that already give this indication that something is not right. So it did recognize that time is in the time column, but it didn't really understand what the units are. So if you click on the units, so just click on this field, you will see that there's the option to either have a unit selected or to import the units from a column. So if you look again to the observed data file, you will see that we have units in a separate column. So we have to select here the option to import units from a column, and then you can select the column. So here the time unit column. And the same for the measurement units. So there we can also select that we do it based on a specific column, which is the measurement unit, and then also the LLOQ. Sorry. So if you always use, for example, the same type of structure, you also have the option to save this configuration. You have here save and load configuration, and the advantage of that is that you don't have to do all of this manual, but it will automatically know what type of columns you are typically using. So you can click here on the save, and you can save this configuration, give it a name, and you can also load it. So then for the next time you would do it, you would just load it instead of manually adapting things. If you have all your information set correctly here, you can click either on the Add Current Sheet or Add All Sheets. So if we only want to add this one data set, we need to make sure that we select the correct one and click Add Current Sheet. And I forgot to adapt the error correctly. So then you will see this import preview where you have here the naming pattern. So your data will be imported and get a name based on what you select here. So you can just select whatever you prefer. You can have a very long name which has all the information from the different columns, or you can give it a very short name. So depending on what you prefer, you can just select something and then it will use that naming pattern. You can also see below here I didn't set the error correctly, so it should be the same. So it should go to the same units as the measurement, and then you shouldn't get the error anymore. So you can just select a naming pattern or make your own naming pattern as you prefer, and then you can click on import. And then you will see all of the observed data appearing below here. You can also reorganize it a bit if you prefer. So if you right click on the observed data, you have the option to create subfolders. So for example, I can say I want a subfolder by study ID if I'm importing multiple studies. And within that, I want a subfolder by organ or compartment. And then it will structure your data a bit to give a better overview of the data. So here we have this data set which has measurements in plasma and also a few data points for endometrium, myometrium, and then ovarium and tuba. However, these two were not used due to the lack of data. We were not able to add these organs to the structure. So we will focus on the endometrium, myometrium, and plasma measurements of this data set. So now we have all the building blocks that we will need to start simulating. So maybe just to ask and to give you some time, but is everyone following until this point, or are there questions or problems? Okay, so then I assume everyone is following along, so please say so if not. Maybe I'll leave this question for someone to reply, as it's not really related to the female reproductive tract.
We can leave it to the end, otherwise, if there is time.
Yeah. So if you want to create, you have files instead of, yeah, so if you just have the files, you can, and that's also perfectly fine. So you can create the folders by right-clicking and then create subfolder. It's just to structure your data a bit, but I don't think it's also in the instructions if you follow the course. So it's just to show you you can do this, but it's really not necessarily. If you just have these type of files, then you're absolutely fine for the course. So in the simulation tab, you will see that there is already this one simulation, which is the one we imported from PKSIM, but doesn't have anything related to the female reproductive tract. If you want to create now a simulation where we also account for this female reproductive tract, you can either make a clone of this one and adapt it, or we can just create a new simulation. So you can right-click on simulations and select create simulation. And then this configuration wizard will open. So you have to give it a name. So again, you can name it how you prefer. And then you see here the configuration of the modules. So on the left, you will see all the modules that you have in your project file. On the right, you will see the ones that are used in your simulation. So you will have to transfer some to the right to make sure that they are used. And what is important with this modules concept is the order of adding the modules. So the first one that we will add in this case will be the PKSIM module, which is the one with the blue icon. And then the second one that we add is the one for the female reproductive tract, which is the orange one, so the MOBI module. And you can just select them and click on add to move them to the right. Now you see that we have first the blue one and then the extension module. So what will happen in the background when creating this simulation, if there are certain parameters or things that are the same or present in both modules, the one that will be in the simulation, the final value will be coming from the last one. So the last building block, which here is the female reproductive tract. If you put them in the opposite order, then it would take lastly, so in the final simulation, give priority to the ones that are in this module. So if you only have different parameters and are not overwriting anything, it doesn't matter. But if you have parameters that are appearing in multiple modules, it's very important in which order you will add them. And you have different types of modules also, so they can be extend or override behavior. So if you want to know more about that, you can go into the details. So that also affects a bit how exactly they are combined. Then if you click on the modules, you will see something switching here in the bottom. So you have to select for each of the module the relevant parameter values and initial conditions. So for our PKSIM module, you will only have one option, which is the metronidazole values. For the female reproductive tract module, you will see, for example, that the parameter values are still default ones, where we want to use the ones that we adapted for our compound. And in case that you have multiple compounds in the same project, you would also see them here and be able to select which one you want to use. So make sure that you have both parameter values and initial conditions selected for metronidazole. And then you can click next. So then we need to select also which individual and which expression profiles we want to use. So here we have only the female or the woman individual, which is already selected. And we still want to use two expression profiles that contain all the information of these two enzymes and their respective expression in all of the default organs. So you can select them and click Add. So then you will see them on the right, so similar like the modules, and you can click OK to create the simulation, and then the software will start combining all your different modules and building blocks into a single PBPK model. So then you get here your simulation. If you are interested to see a bit more what is now exactly in my simulation, you can double click on it to open it. And you will see here all the different parameters and structures that are present. For example, if I open the organism, which is containing all the different organs, you will see that we have here the combination of typical organs, so the arterial blood, the bone, the brain, but then also breast, cervicovaginal fluid, cervix. So it's really the combination of our two modules, the basic PBPK model and then the extension module that we have in this specific simulation. And you can also on the right here see that for all the different parameters, there is also an indication of where they are coming from, so that you can find back that this one, for example, is taken from our base PBPK model. But if we look at the breast, you will see that it indicates that it's coming from our extension module. If you want to run a simulation and it is the first time that you will run it, you can click on Run. You can also, if you already did it and want to change something, click on Define Settings and Run. And then you will get this option to select what you would like to simulate. So we can, for example, if you search for tissues, so you can use this bar on the right top to search to make it a bit easier to find things. Another thing that you can do to make it easier to find what you're looking for is if you hover over one of the column names, you will see this little filter thing appearing on the right. If you click on it, you can also select things. So for example, if I select here the tissue compartments of the female reproductive tract, so the breast, cervix, endometrium, and then you would have to scroll a little bit to find the others, so myometrium, and also the vagina, and you click OK. Then you will see that it's only showing me the tissue concentrations in its respective containers, so you can use that to find what you would like to simulate. You can just select one if you're interested in one specific, or you can select all of them. I will select all of them for this example. So these are all the tissue concentrations that I have. Then besides tissue concentrations, so if I clear this filters again, I would also like to see the fluids. I can remove the selections that I made before. And I can select the cervicovaginal fluid and the uterine fluid. And then you see for these two, so we have either option amount or concentration. So I want to know the concentration in the fluid. So sorry, there was a question. How did you open the simulation settings again? Yeah, so if you had already simulated, you can click here on the top on define settings and run. So in the run and analyze tab, and then define settings and run. And then you will get this screen again and be able to adapt it to what you didn't add before. So we will select also concentration in this fluid containers. And
Nina, I see that we do have a bit of time, so because someone was asking the question, can you show again how you selected the tissue?
Yes.
Thank you.
So we have here this thing where you can click and then you can type. So, and I already know that they are called with name tissue. So if you understand a bit like how these observers are built, you will recognize how they look and it will be easier to search, but you can search for anything that you want. So I want to see tissue concentration, and you see there's tissue concentration in any possible compartments. You can also already select them here, or just to give you another option how you can navigate and find things, you can also hover over this name, and then you can, instead of selecting all, select some specific ones like the breast, cervix, endometrium, and then go a bit down to find myometrium, and completely down to find the vagina. And then you have all 5 of them, so the 5 tissue concentrations here. And you can select them by clicking here. And similarly, you can go in the same selection window, and instead of selecting the tissue compartment, selecting the fluid compartments, which are the uterine and the cervicovaginal fluid. And then you see that we have either amount or concentration. So I want to see the concentration for both, so not only selecting concentration. And then we also want to see the plasma concentration. So if you have no idea how to search for it, you could just search plasma. Then you will see that there is still really a lot, and maybe more than you would like to see. So because there is plasma compartment present in each of the organs. However, you see here already that so it's the first one that we want to see, but you could just navigate and see, okay, it's showing all organs, so maybe I want to filter for a specific organ. So if you want to simulate plasma and all the different female reproductive tract tissues and fluids, you should have plasma here. You should have then tissue concentration 5 times. So for breast, vagina, cervix, myometrium, and endometrium. And you should have 2 concentrations for the fluid compartments. And also here you have the option within a project to make them defaults, and then in another simulation load from default, so you don't have to go through this process of searching things every time you do a new simulation. You could click make defaults, and then if I want to do another simulation, I load them without having to select them again. If you have them selected, you can click OK. And it will start running your simulation. And you will see here all the different simulated results. Of course, we also want to know how this compares to what we have observed. So then you go to your observed data here, and if you created subfolders, you can open them and find the ones that you would like to add. Or you could also add entire folders. Here I don't want to add the ovarium or tuba concentrations as we didn't simulate those. So to add one, you click on them and you drag and drop them into this screen where you have the simulation result. So I'm adding endometrium, then also the myometrium and the plasma concentration. And then you will see that there is a very, very busy plot. So to make it a bit easier to see what exactly is in there and what data should be compared with which line, you can also play with this chart editor. For example, here you have the curve and axis settings where you can pick colors and adapt them a bit. So for each of the lines, you can click on it and select the color. Or if you want to match something, so for example, we have here the endometrium observed, and we also have the endometrium predicted, so I can drag and drop this color from one to another to make them the same color, and do the same for the myometrium, and also for the plasma concentration, which will then color so your points and your line for predicted and observed in the same color. You can also say, okay, I actually don't want to see all of this. I want to see only maybe myometrium, endometrium, and plasma, where I have some measurements available, so that you can unselect the visible. So you can format your plots how you like. So there's another question. What is the difference between drag and drag observer? So I'm not entirely sure where we are speaking them. I think maybe what you mean is in here. So these are the things that you can, so what we have here, probably you mean that. So these are all things that you can simulate, and you will see that there's this drag and observer row where you have inputs that are really observers, and then there's indeed like drag or metabolite, which are not really observers, and that's, well, it's a bit more technical, let's say, but you have, if you open modules, you also have this observer building block, and if you go in there, you can also define your own observers. So it has to do with how these things that you can see or simulate are defined within the software, to give a very brief answer. But yeah, I think the details maybe also, I would refer you to documentation or another course on observers specifically. So you have this plot here. If you would like to move, for example, this information, you can also move it to the bottom. You can give it a title, so you can play with it a bit to make it more appealing. And then besides this result, which is the typical concentration time profile, and so maybe another important thing, you can adapt the units to anything you prefer and change it between linear or a log scale as you like. Then we also have this predicted versus observed curve, where you see easily with the different color here for the different tissues how the prediction is. If you don't see points here, then you need to go to the observed data tab and then make sure that they are linked here. So your observed data should always be linked to simulated output. If we did the mapping correctly of your observed data, this should happen automatically, but sometimes it doesn't, and then you can just select here, and after that it will appear in this plot. You see the individual points and you see the line, which is the unity line. You can also, if you right click anywhere in the plot, then select add deviation line. For example, to visualize, I want to see a two-fold deviation fault error, then you click two-fold and it gives you, with the dotted lines, a two-fold error, and you see that all our points are within two-fold. And a bit similar, you also have this residuals versus time plot where you can have a look with, again, different colors for the different data points. So with that, we have our simulation. We have compared it to observed data, and we are actually ready with the hands-on part that we aim to do. There was another question. So yes, you can optimize a model in MOBI, and just like in PBPK, you have the parameter identification. So if you're not happy with this fit, you could just right click on it and then select start parameter identification, and there select the parameters that you would like to adapt. Or you could also manually in the simulation go into your parameters and say, okay, I have maybe an alternative value for any of the parameters that I want to test, and you can just directly put it here and see if you run again what the effect is on your simulation. Okay, so for the deviation line, so you have this predicted versus observed plot, and you can right click on it, so just anywhere in the plot, and then you can click add deviation lines. And then you can put anything, so any value that you would like. So I have put a two-fold, which is often used, but if you want something more strict or something broader for your application, you can just add it here. If you don't see anything in your plot, despite that you think you added it, you can check here. If you open these things, you will see the lines and the observed and the data. And you can also select whether it's used or not. So sometimes you have to select it here to make sure it's going to be used in the plot. Yes, if you don't have any observed data for the tissue, then you cannot do parameter identification. So you would need any type of data if you want to start fitting a model with PBPK modeling. So one thing you could do is look into similar models or something like that, or compounds with similar behavior and fit based on that. But of course, if you don't have any observed data, then you will always have this uncertainty still left in the model. I'm not sure I got the question. Is the tissue observer here intracellular interstitial? No, the tissue is not just a sum of all of those. I don't exactly remember what by heart what exactly the tissue observers, but it's it's two of them, I think. I would have to check into the documentation. Maybe, I don't know, Sophie or Natalie, if you know by heart. But you can definitely find this in the documentation or go into the observers and have a look for this specific observer and see the formula that is used for it. Can I use it if I know the structure of the molecule? Yes, so in general, PBPK modeling can always be used if you don't have any observed data. You can always make a prediction if you have, of course, the input parameters, or at least have a way to estimate the input parameters. So you could use, if you have the default physicochemical properties, you can use our R script to generate the female reproductive tract parameters, and you can just use this structure to make a prediction. But then, of course, without any data to compare to, you don't know whether the prediction is good or bad, but you can always make a prediction with PBPK without having observed data. And yes, we have also different courses available. So depending on whether you're from industry or academia, it depends a bit whether they are free or not. But we have a lot of courses available on Mobi that go really from very easy to more complex scenarios. And I think Natalie will make later on also a little bit of an announcement on some.
Okay. And I think it's probably the right moment to make that announcement. So yes, as Nina was saying, there are some Mobi course on the Talent LMS. And also, if you are a company and you want us to provide some courses to you, and that's something that we do regularly, we can also customize it to your need. And finally, and it's really out of the press, we are now planning 1 week training, Mobi training in the summer. It will be the week of the 29th of June. So 29th of June to the 3rd of July, where it will be 4 full days of Mobi training, so that by the end, hopefully, you will feel much more comfortable working with Mobi.
And yes, the recording will become available later on. So you can rewatch it, and if you want to go through the entire steps of the course, maybe a bit slower and do it on your own pace, you can also go into the online course and just follow that one step by step. So it has explanations of everything, and it should also work.
Regarding the training course, please, you can send a message at training@𝐻𝐞Labs.com and we will come back to you. Otherwise, you can go in our Talent LMS to see the course. As Nina was saying, for academic, the courses are free. And for the week-long training, this is not yet fully defined.
So for R suite, so if you're referring to the with pSuite R and 𝐻𝐞Labs R packages, they are let's say completely complementary with using PKSIM, Mobi, and R. So usually it's really combination of the different tools that are used. So like we started here in PKSIM to build the base PBPK model, then went to Mobi to extend it. So one thing we often do is then next go to R, where you have also the option to run the simulations. You can also adapt them. You can do sensitivity or parameter identification as well. And you have a lot of different and even more compared to Mobi functions related to plotting. But you cannot, at least at the moment for now, not start completely in R without opening PKSIM or Mobi at all. So you would always need some kind of basic structure, but I could, for example, export this one to R and then in R say, okay, now I want to simulate another dose or something different, or another compartment that I want to simulate, or I want to make a lot of different plots, do the parameter identification, then yes, you can do those in R. But they are a bit different in functionalities, and there are some overlapping ones. Okay, so maybe I will go back to the presentation then for the final concluding slides. Okay. So just as a reminder, so what we did not learn in this course is the base PBPK model, but you have this available in the online course if you are interested. Then we did the part where you extended the PBPK model in MOBI for the female reproductive tract extension module, and we simulated the different tissue and fluid concentrations and made a comparison to the observed data. And then we didn't do that again today, but in the online course, you also have another extension following after this step where we do the local administration then in the vaginal administration in that example. So all of these models are also available via GitHub, so you can find the extension modules that you can use. You can also find, for example, for the components that we use to develop this module, some evaluation reports where you can see different results and the input data for the different modules. You can also find a link there to the training course. So that's all on GitHub and it's freely available for you. So to conclude, this extension model really enables to do PBPK model for any compound that targets the female reproductive tract or that is administered locally in the female reproductive tract. I hope you will agree with me that this modular concepts with OSP makes it quite easy to do this for a new compound. You don't really have to understand all the options in MOBI and how to work in MOBI to just use a module that is already developed. So you can find this model on GitHub, it's for free and it can be used to any base PBPK model. And just as a final recap, so why we are doing this work at the first place. So women's health in general has been largely understudied, especially in the past. So within 𝐼𝐶 Labs, we are very happy to be driving this field forward, and we do think that this work and this module forms a small but very important step towards more equality and representation in modeling, and we really hope that this will also, let's say, be used further. So please use it for your own projects and also work further if you have more data that might not be available to us at this moment. Also feel free to contribute to the OSP community and to further improve these models, and hopefully together let's drive this field even further. And just a small side note, so besides this modeling work, we also developed a Shiny app based on this work. So if you are interested to see what can be done with modeling, but you don't really want to learn how to do PBPK modeling, then this Shiny app is ideal and you can open it. You don't need any modeling experience. You can just select a compound, select an administration route, and then compare how the drug exposure is in the different compartments when you do different types of administration. So you can, for example, compare an oral to a vaginal administration and see how that affects the drug exposure. So again, a QR code you can scan and the link here available. So with that, I would like to conclude for today's webinar. You have here also the 3 QR codes again, if you would like to have a look at the app, the GitHub repository, or the Talent LMS course. And if you have any questions, I'm happy to answer more questions today, or you can also contact us on the training@𝐼𝐶Labs.com.
And so thank you, Nina and Sophie. So before people gather their thoughts to ask any more questions, thank you very much for everyone's participation. Thank you for your engagement. And again, thank you, Sophie and Nina, for a very nice presentation. What I wanted to say in addition to the week, so the summer MOBI week, Starting next month, every month, we will give a free workshop on 𝐷𝐸. So it's really the first step in 𝐷𝐸. So if you're here, probably you know 𝐷𝐸, but if some of your colleagues want to do their first step in 𝐷𝐸, the first one will be in December 11. We advertised it yesterday, and unfortunately, registration is already full. So we close registration, but there will be another one in January, which will be on Eastern time. So it will be 3 p.m. to 7 p.m. Central European time, meaning that it will be 9 to 1 p.m. Eastern time. And then it will be every month, the second Thursday of the month, one time in Central European time and one time in Eastern time. So, and again, as Nina was saying, if you've got questions, don't hesitate to send us an email or to contact us on LinkedIn. And of course, to follow 𝐸 Labs on LinkedIn so that you are aware of new webinars, new courses, etc. So with that, I think we've got, I know there was a question, but not anymore. So are there any additional questions? And there were a couple of questions that were not really directed to the female reproductive tract. So we've got a bit of time. So feel free to ask the question that you had previously. Okay. So it seems that there are no further questions. So thank you again for attending. And we hope that it was useful for you, and we hope to keep in contact with you. Bye-bye.